Okay, welcome everybody. Today we have Emil Bergholtz from Stockholm University, and he will tell us about the topology of non-Hermitian systems. Whenever you're ready, Emil, go ahead.
Right, thanks a lot for the invitation. So what I will tell you about today is basically based on these two papers. One is a review paper of a sort of booming field when people in condensed matter like myself got to learn about non-Hermitian physics, which is of course something you know a lot more about since a longer time. And this is sort of the interface between these two topics. And then I'm also going to tell you about one idea about using these systems for sensors, non-Hermitian topological sensors. And this is work mainly together with Jan Budich in Dresden and my former PhD student, Flora Kunst, who is now a group leader at Max Planck in Erlangen. But there's been quite a lot of collaborators in the last 4 years. Let's see. Now I have some issues getting, okay, now I got through. So since I'm for another field, people are usually shocked when I talk about non-Hermitian. I guess you're well aware of this effect in your community, right? So, doesn't continue, okay. So, you know, complex energies, if you think about quantum physics, non-unitary time evolution, it's like opening a Pandora's box. Everything, hell breaks loose, essentially. Once you let it out, it's hard to control. Nevertheless, this is highly relevant in a number of ways. And the way I mainly think about it is as effective models of physical systems. So you can think about friction, resistivity, dissipation. This is really everywhere. You really don't have isolated systems. In particular, this appears in classical, mechanical, electrical, robotic, and optical metamaterials. Photonic systems, of course, you have gain and loss all over the place, but also open quantum systems. If you want to think about a Lindblad equation, like people in Stockholm often do, you can notice that the Liouvillean is not Hermitian. It's non-Hermitian. So then, of course, you have a density matrix that time evolves. So it's not exactly the same thing as a non-Hermitian Hamiltonian, but it nevertheless captures the phenomenology of non-Hermitian matrices. If you look at materials, as I often do, you can think about an effective description in terms of finite lifetime states. The standard thing to do in condensed matter is to sort of solve the problem, and then you say, oh, we have some broadening of resonances and spectral lines here. Let's assign finite lifetimes. But it might be that the matrix structure of the dissipation is such that it doesn't really commute with your free Hamiltonian in the first place. There's also lots of ideas of using scattering problems and so on to get, well, in a scattering setup, you definitely get non-Hermitian problems. And sort of what's kind of new, or what people have been looking at in my community for the last couple of years, is the perspective of topological phases and combining that with non-Hermitian phenomena. And it boils down to central mathematical fact. And this is something we are very used to in Hermitian matrices, which is at the heart of topological phases, that we have stability of eigenvalues. So the change in an eigenvalue E is bounded by the largest eigenvalue, the perturbation. And if you don't do non-Hermitian stuff, this is something you tend to take for granted. And this inequality is saturated exactly when we perturb in an eigenstate with that corresponding eigenvalue. However, for non-Hermitian matrices, it works completely differently. So if you have a non-Hermitian n by n matrix, the shift in eigenvalue is bounded instead by the nth root of the norm of the perturbation. You can think about this as eigenvalue if you want, but it's not really. You can have zero eigenvalue and still have a finite boundary here. Someone asks something? Philip?
Yeah, Philip.
Yes,
Yeah.
Olaf, good morning. This condition that you have for the non-Hermitian case, is it for an arbitrary non-Hermitian? Does it get tightened up if the non-Hermitian has an antilinear symmetry?
That's a good question. Presumably, certain symmetries will constrain this. Well, actually, I know some cases when it can constrain it. For instance, for a 3x3 matrix, I know an example where you can have a symmetry which forbids the third root, but it admits the square root. So yes.
There's a small comment. It's a general behavior in the vicinity of an nth order Jordan block.
Exactly.
It comes simply from the Jordan block, independent of any additional symmetries.
Exactly. So that's my next slide. That's brilliant. Now we have it. But so really important here is that already for n equals 2, you have a qualitatively new response. You cannot have a square root because square root for a Hermitian case and square root of a small number is much bigger than the small number itself. And now if we look at large matrices, let n go to infinity, then already an arbitrarily small change can give an order of 1 change in eigenvalues. So you completely rearrange everything in that limit. And we will look in detail from the perspective of topological phases what this means with n equal 2, and then we'll look at large n as well. So here it is, really as was anticipated, a perturbed Jordan block. So n by n matrix where you take ones on the first off diagonal, and then you take an epsilon in the opposite corner. And of course, if you only take the epsilon, then the eigenvalue of that perturbation is 0, but you can think of a Hermitian one where you have an epsilon there too. So I get plus minus epsilon as eigenvalues. So this one we can all diagonalize immediately, right? And the characteristic equation is just minus e to the power n. That's this product of minus e on the diagonal. And then the only other thing that enters is 1, 1, 1, 1 times epsilon. So we add this up to 0. And immediately we get that all energies are proportional to the nth root of epsilon. So we see that not only a single eigenvalue changes, the entire spectrum changes. So now if we have a large n, we essentially get all of the eigenvalues on a unit circle, even if epsilon is arbitrarily small. So this is kind of spectacular unless you have seen it, as many of you of course have, but other people get very surprised by this. So today I'll talk about these epsilon equal to 0, which are called exceptional points, as you were well aware of. They're really interesting and abundant. And this is something which looks like a graphene band structure, but it isn't, because graphene has a Dirac or Weil cone. This is a square root cone. This is absolute value of energies of something which is exceptional points. Then I will discuss a very nice proposal for some years ago about using exceptional points as promising sensors, because these are really sharp, right? Small perturbation gives a big impact in the eigenvalues. So this is for small n. There are certain issues with exceptional point sensors that are discussed in the literature. So I'll go through that briefly. And then tell you about an alternative. It might well be that exceptional point sensors are the answers in the end for sensing. But here's another proposal, and that's using large n. And large n is something that's natural in condensed matter when you have a really large system. So take a tight binding model with n sides. Then you just make it bigger and bigger. And I'll show how to, in a robust way, get a topological signal which is exponentially large in the system size. And that's not based on exceptional points. So first, n equal to interesting and abundant. This is supposed to tell you about interesting, and this is abundant. So here's a minimal example. I'm not sure if I should do this for you, but let's take a 2 by 2 matrix up here with a alpha instead of epsilon now. Could have called it epsilon 2. Eigenvalues are square root plus minus alpha. And the square root, if you think about it in a complex plane, is a little bit more complicated than you're sort of used to. You have this Riemann, double Riemann sheet structure that you have to wind twice around to get back to the same energy. And that's, of course, natural with the square root. So there's a branch point at 0, and there's also a branch cut. And this branch cut will have lots of physical implications. And you should note here that the eigenvectors are non-orthogonal. So if alpha here isn't 1, or absolute value of alpha isn't 1, these will not be orthogonal with the plus and minus. Also, which is particular to non-Hermitian systems, is that left and right eigenvectors are not the same. And in particular, at this exceptional point, alpha equal to 0, both eigenvectors and eigenvalues coalesce. So both eigenvalues here are 0, but you only have one eigenvector, one right and one left. And sort of the right and the left one are then the opposite. It's, for instance, summarized here by Michael Berry in 2004, but the concept was around for at least 50 years or so before that. Kato, Pancharatnam, and many others. So is this relevant for physics? Well, I'll try to give you 2 answers, and I'm sure you can give me many more. One is that yes, they actually have a long history in optics and photonics in particular. And when I was an undergraduate, actually, I heard Michael Berry talking about it about 20 years ago. But at that time, I wasn't able to sort of absorb what the wisdom he was giving out. And there is, in fact, many review articles. Here's a nice one in Science about exceptional points in optics and photonics. So this really has to do with physics. There is also another argument for why it's relevant for physics, and that's the answer to this. Isn't it fine-tuning? Sure, it is fine-tuning. The Jordan block I showed you is very particular matrix. Every matrix doesn't respond extremely sensitively to a perturbation. But they are abundant. So to see that, I think it's very instructive to write down a generic 2-band model. So you can write a Hamiltonian, and I think about Bloch Hamiltonians now as a function of momentum. You could also think about it in terms of other parameters. But write it as on vector D, scalar de Pauli matrices. And there can also be a unit matrix, but since we're interested in band crossings or band touchings, we just throw it away. So D now is a complex vector. It has a real part and an imaginary part. So solving this, you get energies, just square and take the square root. You get the real part squared minus the imaginary part squared, plus 2 times the scalar product between real and imaginary part. And then you ask, how many constraints do you have to have 0 energy? Well, it's actually only 2. This is one real equation, and this is one real equation. So if we only have to solve 2 real equations, we have generic band crossings from only tuning 2 parameters. And this might not sound as remarkable, but it is, at least if you come from the topological context where you're known to Hermitian, used to Hermitian degeneracies that need 3 tuning parameters. And that's why Weil, symmetries, etc., are only found in 3 dimensions. If you want to say that graphene exists in 2 dimensions, yes, that's true, but that depends on PT symmetry. If you break it, you gap out the Dirac on graphene immediately. So exceptional points are much more abundant than degeneracies in the Hermitian case. So both from a physics point of view, from the photonics and so on, they are really important for physics. And this is the theory argument why they are so abundant. So let's just take a random non-Hermitian model and look at the spectrum. And we will find that exceptional points are essentially square roots of wild points. It should be expected from the square root we found in the beginning. So if you look at the absolute value of the energies, which doesn't really have a direct physical implication, but here you see really this sharpness of these exceptional points. But if you look at the real part, which is more physical, or the imaginary part, which is also more physical, they have these branch cuts. And they are sort of forming complementary loops. This was, as far as I know, first pointed out in this preprint by Cosi and Fu. And this wasn't published because I guess the implementation wasn't quite solid. Oh, there's another question.
I'm sorry, I must have missed it. Can you remind us what a Weil point is?
Yeah, a Weil point is essentially k dot sigma. So kx sigma x plus ky sigma y plus kz sigma z. So it's a conical section, half of the Dirac equation. If you have a massless Dirac equation, you can split it into two blocks, and each block is a Weil Fermi.
Oh, okay.
And they have a certain chirality and so on. And in 1929, Hermann Weil suggested that these could be fundamental particles, I guess. And people thought for a long time that neutrinos might be Weil particles, but they weren't, because they have a small mass, because of the neutrino mixing. But these are now found in three-dimensional materials.
Thank you.
They have very specific spectral signatures. And these are sort of reminiscent of the Weil fermions in 3D, but they occur already in 2D. So let's have a closer look at these arcs. It's pretty instructive to understand where they come from. So let's look at this expression for the energy and divide up space such that we take this real part of the expression under square root and divide it into parts of space where parameter space where it's larger than 0 and parts where it's less than 0. So in 2 dimensions, this will form a closed loop. And similarly for the other equation, this is smaller than in some region and larger in some region. The exceptional points, they occur when these two lines intersect, because then we have 0 plus I times 0, which is 0. Okay. But then we also notice that we have Fermi arcs defined as a real part of energy being 0, when this thing under the square root is real and negative. That is when this is 0 and this is negative. So we can look why this is and color it red, and you see that it forms this open arc which ends at exceptional points. If you do the same thing for the imaginary part, if you want, you will find that it's a complementary curve here. So at the exceptional point, you switch between a real and the complex gap, just like at the PT transition that I guess you're very familiar with. So actually these can be observed just as the Fermi arcs in Weil semimetals have been observed recently. So was the case of these Fermi arcs. So here is photonic crystals looked at by an MIT group published in Science 4 years ago. The thing they do is that they look at a certain frequency and they look at the light scattering. And then they change the frequency, so they make cuts in the band structure. So here they go in simulations from a high wavelength to a lower one. And here they have a Fermi arc. So it's an open end line. So here are the experiments. which looks even more convincing, I think, than the theory. But the theory has a non-Hermitian Hamiltonian in it. So here you see the arc structure, looks like a boomerang. So the thing is that otherwise Fermi surfaces are closed, right? And they are not here. And that's a topological feature. That's the branch cut of my initial example. That's the branch cut of the square root, nothing else. If you do the same in 3D, it becomes very interesting for mathematically minded people, because then you get knots. So since you have to tune 2 parameters, in 3 dimensions you have 3 parameters, and the solutions are then line-like. And we have 2 notions of topology combined that we don't have in the Hermitian case, because in the Hermitian case we get generic line-like nodes only in 4D. But of course in D larger than 3, all knots are trivial. You might also ask, what are the corresponding Fermi arcs? Well, they have to connect points on this line, which is now knotted, and it turns out to be the Seifert surface of the knot. So with each knot, there is a set of Seifert surfaces defined, and they are the Fermi arcs of this system. And you can do lots of knot theory and come up with essentially anything in relatively simple models. Nevertheless, I thought that when we did this 3 years ago, I thought that this would probably never be realized in any experiment because it's so out there. But it has been already. First, there were experiments of exceptional rings in coupled waveguides. And later, I would say that this is more like a simulation of a phenomena rather than finding really advanced structure. But in Beijing, there was an experiment in single photon interferometry where you can see these Seifert surfaces and the knotted exceptional lines and so on. So essentially all of these models can be realized in the lab. And since I know you're a lot into symmetries, you can think about general symmetries in non-Hermitian systems. From the condensed matter point of view, we have the Altan-Sinbauer classification. But if you go to non-Hermitian matrices, you instead have the Bernard-Leclerc classification, which they originally said was 43 classes, and later in an updated version said 38. And that's just a matter of definition, how you count your classes. Here's one example that if you have your Hamiltonian, it's related to the Hermitian conjugate of the Hamiltonian. And this is pseudo-hermiticity, so I guess you see this all the time. But if we take this in our example of 2x2 Hamiltonians, you can pick one representation, which is non-trivial, for instance, Pauli X matrix, sigma X. And just do the algebra, and you will find that components of the D vector, the X component and the 0 component have to be real, and the Y and Z has to be imaginary. And if you plug that into the formula, you see that dr di is now 0 because imaginary components and real components are not having any overlap. And the energy is just something like this. So this switches from real to imaginary. Plus a constant term which doesn't have to do with the gap. And of course, PT symmetry works in the same way. Then essentially, if you take PT symmetry as complex conjugation, then you find that you have a real representation, and therefore you just have an imaginary part on the sigma y, the usual representation. So generically, we have one equation less. So we have exceptional d-1 dimensional surfaces and d-dimensional open Fermi volumes. So in 2D, for instance, we have exceptional rings and drumhead states. And this has been shown not only by us, but by many others, essentially at the same time. And then shown in experiment later on. You might ask what happens if you go on with n equals 3 and 4 and so on. And I will only be very brief to not be too lengthy here. So here, what we are doing is taking a 3-band model, which it's a very specific fine-tuned 3-band model. Did someone ask something? No.
No, someone just didn't mute themselves. So.
Okay. Yeah, so if you take such a model and then you perturb it by, if you PT symmetric case, you can still have a stabilized third order EP in 2 dimensions. And if you have some other chiral symmetry, you can get a very different type of EP, which is also stabilized by this other symmetry. So actually, the higher you go in N, the more abundant the non-Hermitian degeneracies are as compared to the Hermitian ones. So in general, to get an nth order EP, you have to have 2n-2 real constraints. It's essentially writing on an upper trigonal form and then having the diagonal to 0. That's what you need to count. You have to have them the same. But for Hermitian degeneracies, you actually need n²-1 constraints. And that's because, well, you essentially have to make it diagonal. You cannot have any off-diagonal elements because that always splits energy eigenvalues. Still, the n equals 3 EPs would be stable only in 4 dimensions. But then symmetry again, for instance, PT symmetry says that we have either real or complex conjugate pairs of energies that cuts the number of parameters by 2. So an nth order EP has codimension n-1. Only need to tune n-1 parameters to get it. And this holds not only for PT, but lots of other symmetries. And here was an example that I showed you, as discussed in these relatively recent papers. This type of different EPs have been discussed in the mathematical literature much earlier, but here we show that they are stabilized by different symmetries. So this is the generic case you get if you respect a certain symmetry. And there is much more on the topological band structure front. You can classify nodal topologies with symmetries. So if you have PT symmetry, here is an example of everything you can have. So you can have second order EPs that have arbitrary genus. And you can knot these surfaces if you want, but mathematicians, of course, care more about the genus when you have surfaces embedded in 3D. You can have third order EPs that are knotted lines, and fourth order EPs are generic, but point-like. I only talked about gapless phases, but there's also new notions of gapped topological phases. For instance, studied by Kawabata et al. In this paper. Interesting thing here is that you can have point gap phases and line gap phases. And a new rich symmetry classification with the Bernard-Leclerc and PT symmetries and so on. You also have a very novel bulk boundary correspondence, and that's described, for instance, in this review paper. And there's lots of experimental platforms. So there is lots of beautiful mathematics here, but some people tend to ask if things can be useful. And that, I think, is a fair question. You know, we can get this in some optics experiment, but does it mean anything? Can we use it for anything? And one brilliant idea here by Jan Wirsig in 2014 was to use it for sensors. It's kind of clear from my introduction that would sort of come, right? But he had a specific idea here on how to use microcavities for single particle detection. And it didn't take long, because in 2017, there were 2 papers here in Nature using exactly this kind of sharp dispersion to say that you get a very good sensing in these optical microcavities. And people got very excited. For instance, what if we can use this to probe the dark universe? If we have square root of an axion coupling, for instance, it's much easier to detect, or if we're third root of a small number, even better. Now, so far, this has not been a revolution. And you might ask why. And there are obviously many different answers to this. One is that it's complicated, and nobody really knows the fate of this, how successful it will be. One answer was provided by Wolfgang Langbein, who said simply no exceptional precision of exceptional point sensors. And his argument, it's very nicely written paper. He pointed out that the measured signal also depends on the eigenstates, which necessarily change dramatically away from exceptional points. So in his little calculation there, he showed that the signal is proportional to square root of epsilon, essentially, times square root of epsilon. One is from the eigenvalue and one is from the eigenstate. And this is equal to epsilon, which is the Hermitian precision. And he claims that this is consistent with experimental data at a closer look. Okay, well, be it. But exceptional point fans sort of strike back. And here is one interesting paper that shows that more generic measurements could actually harness a fundamental advantage of the exceptional point-based sensors. And this is really good, of course. But things are, to me, starting to look a little bit complicated. And since I didn't know anything about sensors, okay, let's try to get some other inspiration. And one of our collaborators, Frank Wilczek, said this quote, which I like more and more all the time. I try to avoid hard work. When things look complicated, that's often a sign that there's a better way to do it. And that's sometimes true, and sometimes it's just false. But we can go on and have a wish list. And a wish list for a sensor would be a single isolated mode, because then the eigenstates wouldn't necessarily change much. If the eigenstates coalesce, they will necessarily change. We want large n, not 2 or 3, but as large as possible. Operational over many orders of magnitude, if possible. No fine-tuning, because the EP sensors are very good if you're exactly at EP. If you're a bit away from it, it's not as good anymore. We would like to have topological robustness, possible to realize with existing building blocks, and practically useful. And I won't come the whole way, but pretty far, I hope. So large n, that's very natural in terms of lattice models, tight binding models. And here is one depicted by Hatano and Nelson from 96. And more inspiration comes from the extremely strong dependence of boundary conditions in certain non-Hermitian topological phases. So here's one example studied in this early paper by our group that showed that we took a certain model on a torus in 2 dimensions, and it has a spectrum that's gray and is gapless. Then we take the same model, cut it off on a cylinder, then it suddenly looks like a Chern insulator with a gapped bulk spectrum and a chiral edge state. And this goes back to the first example that I had, that you have a small perturbation, such as changing the boundary connection between the ends, can have a huge impact on the entire spectrum. And these 2 early papers gave complementary ways of reconciling this. But I won't go into the details because that becomes a little bit technical. But I will mention that about a year after these papers, there was really an avalanche of experiments starting to come based on this bulk boundary correspondence that breaks down. So I put the archive numbers here just to show that they were coming out basically at the same time. The very first one was in the electrical circuits, and then days after was robotic systems, and then quantum walks, and so on. And they all find this strong sensitivity to boundary conditions. So our suggestion was to take a specific topological system, namely a non-Hermitian SSH chain, but with an odd number of sites. And odd is important and unusual. Actually, this is usually protected by a chiral symmetry, which requires that you have an even number of sites, but we cut it. So SSH chain, it has these two orbitals in the unit cell, and it has hopping amplitudes T1 and T2. And here we have an asymmetry gamma in the game. So it's not the same hopping to the left as hopping to the right. The great thing with this is that when an odd number of sites for any parameter value, there is an isolated mode, or there are certain points in parameter space where there are other states coming down. But for most of parameter values, there's a gap and there's an isolated mode. Moreover, it's possible to analytically write down what this state is, and it's a boundary state. It's localized either to the left of the chain or to the right of the chain, depending on the parameters. In particular, the right eigenvector does not have to be localized to the same boundary as the left eigenvector. So here are the exponential factors. Don't bother the details. I could show you more detail if someone wants to, but it's relatively easy to find. So the thing we could sense would then be to couple the two ends. So buckle up the chain and have some way of changing the matrix element, coupling the two ends from 0 to something finite. And since we have a single isolated mode, we can calculate the energy shift in perturbation theory. It's just the bi-orthogonal expectation value of the shape of the change in the Hamiltonian. So if you do this, it's just geometric series, you find that this is exponential. And also for Hermitian system, this would be exponential. It's just that alpha would be negative then, so it's exponentially small. That wouldn't help us. But here we find that alpha is positive, so exponentially large, if and only if the left and the right states are located at opposite boundaries. And this happens in a large and finite parameter space. So let's get the intuition for this. Well, case one, left and right eigenstates are at the same boundary. This is always the case in the Hermitian case. So both right and left sit here on the same side. Then this matrix element is exponentially small. It's gamma times order 1 from one of the wave functions times an exponential tail of the other one. So it's exponentially small times gamma. But the overlap between the left and right states is of order 1 because they sit at the same boundary. So the shift in energy, which is the ratio between these, is exponentially small times gamma. That's expected case. The interesting case is if left and right are at opposite boundaries. So here left, let's say, and here is right. Then this matrix element is of order 1 times gamma, because this is of order 1 here, and this is of order 1 here, and they are coupled, so you get the factor of gamma. However, the overlap between left and right state, they're at opposite boundaries, is now exponentially small. They just have exponential tails that meet and overlap a little bit. So the shift in energy is the ratio between this and that's exponentially large times gamma. That's it. So here's the numerical check. And the solid lines here are our perturbative results, and the dots are exact numerics for finite chains. So we plot shift in energy on an exponential scale versus the system size. So let's look at the black line. That's where I took a perturbation gamma equal to 10 to the minus 14, the smallest our computer managed, or our laptop. You can do a better computer, you can get a better result. So for a small system, okay, you get a shift of 10 to the minus 14. But if you take 100 sites in your chain, you're up to order 0.1. And all of these dots are exactly on the perturbative line. But here they start to deviate. Why do they deviate? Well, that's a gap in our system. That's when we start to have higher order corrections. So eventually, if you make the system big enough for an arbitrarily small perturbation, this will be something that mixes with the gap. So it's only operational between here and here, but still in this case, that's like 12 or 13 orders of magnitude. And if we want an even better sensor to have a weaker signal, then we don't have 150 sites, we have 300 sites or 600 or whatever we want, given the precision we are interested in. But of course, we don't want it too sensitive, because then it gets screwed up in the gap right away. So what did we actually get? Well, we get a linear shift with an exponentially large prefactor rather than nth root. So this is not what I started out with. Right? So this is a stable effect with no fine-tuning. This is what we got. And this is the exceptional point effect, which requires fine-tuning. At a certain detection limit, of course, they are equally good. But this scales very well in the big system limit. So first order perturbation theory worked, and in a way, that shows the assertion that there was no significant change in the eigenstates, because otherwise it wouldn't have worked. And there's a single isolated mode, so the signal should also be exponential in system size, because again, the eigenstates don't change at the same order. And this relies on other states being proximate to higher order EP due to what's called the skin effect. And I didn't have time to tell you what the skin effect is, but the skin effect is essentially all eigenstates of the system pile up at the boundary. And if you would let them through to the other side, you would get Bloch states which are extended. And that's why you get this huge shift in eigenvalues. So one can relate this to a little bit running out of time, but this works well with disorder. It's not sensitive to local disorder. And it turns out that there's a topological protection. If you would have seen SSH chains before, you know, it's a symmetry protected topological phase, which depends on the winding in the plane of the vector D, which is only protected if you have chiral symmetry. If it's not chiral symmetry, you go out of the plane and then the winding is not quantized. But this is a different type of topology. This is the winding of the eigenvalues in the complex plane. So it's a topological number that's similar to Chern number in that it doesn't rely on symmetries, but is uniquely non-Hermitian. In Hermitian systems, energies simply don't wind in the complex plane. And if you calculate this integral, you find that it's finite exactly in the same region as we get amplification of the signal. So implementations, there are many possibilities. Well, the easiest one we could come up with is to take the original, essentially the original suggestion of an EP sensor and use that as a unit cell, and then have a chiral coupler to another unit cell. And in that way, you can successively build up an SSH chain. And this open boundary condition model is already implemented in other classical metamaterials, electrical circuits and robots and so on. So they could also be useful, perhaps, or some quantum system. It's unclear which one will eventually be the best, if any. There are also other lattice models. You can have gain and loss as non-Hermitian part instead of asymmetric hopping. That's easier in some sense, but that's not enough, it turns out. Then you need spin-orbit coupling, as implied by these terms. But we need something. We need some symmetry breaking because the states need to pile up at one side or the other. And in particular, to get non-trivial non-Hermitian effects, of course, we cannot have the anti-Hermitian part commuting with the Hermitian part. So on this wish list, we got all the way to practically useful, which I still have absolutely no idea about. But I think this is interesting enough to push on. And well, it's been pandemic. We put this out during the pandemic, and interactions with experimentalists have been scarce, to put it mildly. I hope that will change and that someone is interested in trying to see if this is useful or not. So let me just briefly conclude. So non-hermeticity really gives qualitatively.
We have a question from Philip, or do you want to wait until the end, Philip?
At the end.
Okay.
Okay, then just very quickly here, that there are intriguing prospects. We don't know if they will eventually work. And there are really lots of open questions that remain. Also other types of applications, for instance. Quantum systems, effective descriptions, and so on. That's it. Yes.
Thank you very much. Let's thank Emil for the nice talk and questions. Philip.
Yes, Emil, thank you very much. Your discussion of introducing a little parameter epsilon to a Jordan block matrix affects every eigenvalue. There's something similar that I've been dealing with. There's a class of functions called second order associated Legendre functions. Instead of the PLM, they're the QLM, only with L and M non-integer. And if you take a particular Q where the upper index is -1/2 minus K, and the lower index is -1/2 plus I tau, which makes it a conical function, then as long as K is non-zero, the function has an infinite number of poles in the complex plane. But then when you let K equal 0, all the poles look like they're going to move to the imaginary tau axis, but they all have residues that vanish. And you're left with only one pole. So you have one pole in the complex tau plane when K is 0, and an infinite number of poles in the complex tau plane when K is not 0. So it looks a little bit like K equals 0 is an exceptional point. Anyway, that was the comment.
Okay.
May I ask a question?
Sure, Uwe.
Yes.
Yes, you had this one slide where you have the relation of the decay coefficients, one times with this exponent 2n and this other times n or something like this. Can you go back to this?
Yeah, let's see. I have some issues here with my. So this one, is that what you meant?
No, there had been this just.
This
one later, maybe one or once more later. Just yes, where this intuition, the next, I think. No, one more. Yes, this one. Yes, exactly. Did you try to figure out there? It looks very much like having a kind of duality between your two models. That you have some parameter mapping, because you can just rescale it. When you look on the left-hand side, you can just identify this gamma on the left-hand side and on the right-hand side, and by rescaling. So you will have a kind of renormalization property there in your model. So you will have a kind of duality between your two models or approaches. And there should be very nice additional feature underlying it. Did you try to figure this out? Or?
No, but I think there's this kind of, you can think about having an imaginary flux that you can tune essentially between open or almost open and closed boundary conditions, right? And there might be a mapping like that.
No, I'm just as a first step, just think about mathematical mapping, and afterwards just try to figure out what kind of experiment or concrete physics to relate it.
Yeah,
but it's up to now you didn't do this.
No,
okay.
but I know that there are people that have been working on such mappings.
Okay.
But not in this particular case, but.
Yeah, I see. Okay. Thank you very much. Very beautiful talk. Very nice, interesting talk.
Thanks.
More questions, comments? I have a simple one just on terminology. What is robotic metamaterial? Yeah,
well, it's essentially it's this big robots that they have. They make, well, let's see. You can see these guys. You can even see what it is. It looks like almost like a Lego or something, and they have some way of pushing energy into it. So there's the Amsterdam group that's working on with this. I think Vitelli was not involved in this, but there has been this. People, they have very nice robots to play with, both Hermitian and non-Hermitian.
Okay, thank you.
Yes.
More
Otherwise, mechanics with friction is a typical model of non-Hermitian system also.
Okay. More questions, comments? Well, if not, let's thank Emil again for this very nice talk. Thank you very much, Emil.
Thanks.
Thanks, Emil.